Here we will examine the physiology of blood pressure. So this diagram shows us blood pressure on the vertical axis in millimeters of mercury, and the different types of blood vessels on the horizontal axis. As we can see from the graph, blood pressure is highest in the arteries, particularly in the aorta, and from there it begins to drop off as it moves further from the heart. We see the steepest drop in blood pressure in the arterioles, and the blood pressure in the vena cava, which are returning blood to the right atrium, is extremely low. It's approximately 1 millimeter of mercury in terms of pressure. So let's examine arterial blood pressure first. So arterial blood pressure is pulsatile, which means that it rises and falls with the heart's periods of contraction and relaxation. Arterial pressure is highest during systole, when the ventricles are contracting, and lowest during diastole, when the ventricles are relaxing. Arterial blood pressure is determined by two factors. The first is the elasticity of the vessels. We saw that there was a good amount of elastic connective tissue in the external elastic membrane of the tunica media, which made these vessels particularly stretchy. The other is the volume of blood ejected into the arteries by the ventricles during the cardiac cycle. More blood ejected into the arteries means higher pressures, and less blood ejected into the arteries means lower pressures. Because arterial pressure is pulsatile, we see that the pressure is different at different points during the cardiac cycle. As we mentioned before, arterial pressure is highest during systole, when the ventricles are contracting, and arterial pressure is lowest during diastole, when the ventricles relax. So, seeing as the pressure changes during the cardiac cycle, we can take a weighted average of the systolic and diastolic pressures that we see in the arteries, which is what is referred to as the mean arterial pressure. So this is the average of the systolic and diastolic pressures. We see that mean arterial pressure can be calculated as systolic blood pressure, or SBP, minus the diastolic blood pressure, DBP, divide that by 3, and then add to it the diastolic blood pressure. So the reason that I have the first part of the equation in purple is that when you're calculating it, calculate that first. And then that number that it gives you, add diastolic pressure to that, and that will give you the correct mean arterial pressure. If you do it in any other order, it will give you the wrong number, and you'll have the wrong calculation for mean arterial pressure. So as a reminder here, the systolic blood pressure, or the SBP, is the pressure found or observed in the aorta during ventricular contraction. So on average, in a healthy adult, this is approximately 120 millimeters of mercury. The diastolic blood pressure, or the DBP, is the pressure that is exerted in the aorta during ventricular contraction. On average, this is about 80 millimeters of mercury in a healthy adult. We can also determine the pulse pressure, which is the systolic blood pressure minus the diastolic blood pressure. So therefore, the pulse pressure is the difference between the systolic and diastolic pressures. So if we have an average systolic blood pressure of 120 millimeters of mercury and an average diastolic blood pressure of 80 millimeters of mercury, a typical pulse pressure would be 120 minus 80, which is equal to 40 millimeters of mercury. So that would be our pulse pressure, is 40 millimeters of mercury in that example calculation there. So that means we can simplify the previous equation to pulse pressure divided by 3, and then add diastolic pressure to it. So I'd like you to take a moment and give you a few practice problems for calculating mean arterial pressure, given the following values that you see here on the screen. So please pause the video for a moment while you are working on these, and resume the video to receive the answers to them. So for the top practice problem, the answer is 93.3 millimeters of mercury. For the middle practice problem, the answer is 114 millimeters of mercury. And for the bottom practice problem, the answer is 129.66 millimeters of mercury. So in this problem, I'd like you to calculate systolic blood pressure given the following two variables. So again, please pause the video for a moment while you are working on these, and resume the video to receive the answer. So we have to approach this problem a little differently. Since pulse pressure is equal to the systolic blood pressure minus the diastolic blood pressure, and we have been given pulse pressure and diastolic pressure, we would simply add the diastolic blood pressure to the pulse pressure, which will give us the systolic blood pressure. So the correct answer here is that the systolic blood pressure is 152 millimeters of mercury. You can easily check your work by taking the systolic blood pressure of 152 millimeters of mercury and subtracting the diastolic blood pressure of 88 millimeters of mercury from it, which gives us the pulse pressure of 64 millimeters of mercury. So let's take a moment and examine some of the factors that increase mean arterial pressure, or MAP. Increases in stroke volume and heart rate will increase cardiac output. So assuming resistance stays the same, this will increase mean arterial pressure. So know that stroke volume would decrease during hemorrhaging because blood loss would decrease blood volume as well as stroke volume, or when sweating excessively. So as that would cause massive water loss from the blood, which would also decrease blood volume. We also see that blood vessel constriction due to decreased diameter of the vessels, increased blood viscosity by increasing hematocrit or decreasing plasma volume, or by increasing blood vessel length, we will increase the resistance, which is shown on this diagram as the total peripheral resistance. So assuming that cardiac output stays the same, an increase in resistance will increase the mean arterial pressure. So blood pressure, although it doesn't show it on this particular figure here, is calculated as cardiac output multiplied by the resistance. So moving on to the superficial pulse points, I would like to ask you to please familiarize yourself with these superficial pulse points. This is where arterial blood pressure pulses can be felt through the skin. So these are particularly helpful to know because compression of any of these arteries reduces the blood flow downstream to any arteries that are connected with them, which is particularly useful in dealing with major wounds because this can slow blood flow and slow down hemorrhaging if somebody is injured. Because the dorsalis pedis artery is the furthest from the heart, it tends to be the weakest of the arterial pulse points. So now that we have examined arterial blood pressure, we can take a look at capillary blood pressure. So capillary blood pressure, as we see kind of in the middle of this chart here, is approximately 35 millimeters of mercury at the beginning of most capillary beds, and at the end of the capillary bed is about 18 millimeters of mercury. So pressures any higher than 35 millimeters of mercury would rupture the capillaries due to how thin their walls are. And finally, we can examine venous blood pressure. So venous blood pressure, starting at the venules, is about 18 millimeters of mercury to just above zero, like roughly between 0 and 1 millimeters of mercury in the vena cava. The low pressure in the veins is due to two things. The first is the resistance or the friction along the length of all of the blood vessels that the blood has just traveled through has slowed blood flow considerably. The second is that blood is far from the initial pumping action of the heart, in particular the pumping action of the ventricles, because that's what propelled the blood into the arteries to begin with. So due to this low pressure, how is it that blood is driven through the veins? So we saw that it was driven through the arteries by the pumping action of the ventricles, but how does blood still keep flowing in the veins even though the pressure is extremely low, particularly in the vena cava? And the answer to that question is that skeletal muscle contraction squeezes blood through the veins. So as skeletal muscles contract, they squeeze the walls of nearby veins, which pushes the blood through them. So recall also that veins have venous valves, and the valves, working very similarly to the semilunar valves that we see between the ventricles and the large arteries of the heart, the valves are ensuring that blood does not backflow and will continue moving towards the heart. So any blood that flows backwards will close the valves, ensuring that blood will only really move forward, that is, towards the heart, through the open valves. So last but not least, we can also measure blood pressure using a blood pressure cuff called a sphygmomanometer and a stethoscope. So we can place the cuff around the upper arm, for example, and place the stethoscope at the end of the cuff near the elbow joint and listen for the sound of blood moving through the arteries, which in this particular example here would be the brachial artery. The cuff would typically be inflated to a pressure that would be higher than the arterial blood pressure, which would then completely prevent blood from moving through the artery, and we would hear no sound through the stethoscope, which is what the very left side of this diagram is showing us. And then we would slowly start to let the pressure out of the cuff. We see that when the cuff pressure is equal to the arterial blood pressure, we would hear the first sound, called the first Korotkov sound, as the systolic pressure would force the artery open and blood would flow very turbulently past the cuff. This would be then read on the sphygmomanometer, or the blood pressure cuff, as our systolic pressure. The Korotkov sounds would then be heard at every systole, that is, they would be heard with every heartbeat. And finally, the last Korotkov sound would be heard when the cuff pressure equaled the diastolic pressure, as that artery would then be completely open and the blood flow would not be turbulent anymore, it would flow much more smoothly. So when the cuff pressure falls less than the diastolic pressure, we would then hear no sound, and that last sound that we heard would be taken as our diastolic pressure.